Okay. Sorry.
Thanks. All right. Welcome everybody for to my thesis talk. Today I'm going to be talking about visual aided LiDAR-Inertial odometry system in challenging subterranean environments. Before I begin, I would like to thank my committee member to be here and give me valuable advice throughout the thesis. All right. So here is the outline of today's talk. At the beginning, I will be talking about the background and motivation of this work, why is this important and why are we doing this? And then I will move on to the hardware system that we implemented our method on. And next, I'll start talking about approach. First, a degeneracy and failure detection method for both LiDAR and visual odometry is introduced. And then the depth enhanced VIO pipeline will be shown. And then finally, the fusion of VIO and the original LiDAR-Inertial odometry using the degeneracy module will be presented. And at the very end, we will show some experimental results for the degeneracy and failure detection, as well as the map and trajectory of the final pipeline in some challenging environments. First, let's talk about the background and motivation. Situational awareness is a popular topic recently in both the research community and the industry. So because it is essential for autonomous robots to fulfill complex and dangerous missions, such as perception in subterranean environments, industrial inspection, and search and rescue. In the DARPA Subterranean challenge, a fleet of robots are sent to unknown underground environments to autonomously explore, detect a predefined set of artifacts, and report the type and location of those artifacts back to the base station. Simultaneous localization and mapping, or short for SLAM, is one of the fundamental components of the autonomous robotic exploration. The goal of SLAM is to create an accurate map of the environment and provide robust state estimation to the robot. The accuracy and robustness of SLAM also determine the performance of many downstream components. For example, control algorithms rely on high frequency state estimation in order to keep the drones and ground robots from crashing. Exploration planning needs a local and global map to find a reasonable frontiers and waypoints for the robots to explore. And finally, artifact localization needs an accurate pose and map information to localize the items within the area bound. In the previous challenges, LiDAR-based odometry methods were chosen because of the high fidelity 3D measurements from the LiDAR sensors. So in the first challenge, which is the tunnel circuit, we adopt to use LOM as our state estimation method. And in the later ones, we switch to the LiDAR-only version of super odometry for our robots. Although LiDAR-based odometry methods present promising performance in the majority of the scenarios, they suffer to provide robust estimation when encounter structureless environments. So here we show two examples. On the left, it's an elevator shaft where Z direction motion is felt to be estimated. And on the right, for a long corridor, we can also see a failure of scan registration. So these challenging scenes are common in the competition and need to be dealt with. The natural approach to solve this issue is to add additional odometry source to the state estimation system. For our setup, vision-based odometry is one accessible approach and can effectively provide constraints in geometrically degraded environments. However, vision-based method usually have a larger drift rate comparing with the LiDAR-based method. Vision-based method also can fail in perceptually degraded settings, such as sudden photometric change or insufficient illumination, etc. Thus, the problem of how to combine different sources of odometry is still worth discussion. So here we show two previous work on on the fusion of visual odometry and LiDAR odometry. The first one, VLOM, which is a loosely coupled method, adopt for a sequential framework where visual odometry will provide LiDAR odometry a initial guess. And on the bottom, the LV-ISM, which is a tightly coupled method, jointly optimize the robot pose using both camera and LiDAR information. In our view, the desired solution should prefer the better odometry given the current environment solution. So to reach this goal, degeneracy detection method for both LiDAR and visual odometry are necessary, as well as a robust switching mechanism between the odometry sources in the state estimation pipeline. So now we sum up the contribution of of the thesis. First, a degeneracy and failure detection method for both LiDAR and visual odometry systems is presented. And then the hardware and software design of a LiDAR depth enhanced VIO system will be shown. And finally, a visionated LiDAR-Inertial odometry pipeline is presented. Okay, now we're done with the background and motivation. Let's move on to the hardware system. The algorithm is tested on various hardware systems, including the Spot payload, the DS drones, and Canary drones for the Team Explorer's DARPA Subterranean Challenge robot setup. Our thesis mainly focuses on the DS drone setup, which is in the middle. An overview of the hardware system is presented, and then critical components related to state estimation will be further discussed. Specifically, this chapter will be expand on the time synchronization between all the sensors and getting the best image quality to support visual inertial odometry. Now let's move on to the time synchronization. Time synchronization is critical for the performance of state estimation systems, as the algorithm often needs to perform data association and sensor fusion between multiple sensing capabilities. Though online temporal offset estimation methods exist, SLAM systems are generally less stable and have higher drift rates when there are no synchronization between sensors. For our setup, we need to have synchronized sensor readings for camera images, IMU, and Valentine laser scans. So here is the diagram of our DS drone setup. So here, we choose the IMU internal clock as our time server, and all the other sensors synchronize their timestamps to the IMU time server. To synchronize the Valentine to IMU clock, a PBS signal from the IMU, the PBS stands for pulse per second, from the IMU, which is based on its internal clock, is directed to the Valentine. And on the NUC computer side, whenever it receives a PBS IMU data packet, it will create an NMEA message with timestamp rounded to the closest second and sends that message to the Valentine through Ethernet connection. And for the UI camera, the system uses a TNC to manage camera external triggering signal. The IMU PBS signal is wired to a GPIO pin on TNC, so it has the IMU internal clock information available. Upon image request, the UI driver sends a start camera trigger command to the TNC, and then it will generate a 15 Hz camera trigger signal starting from the next IMU PBS. This ensures that the camera grabs frame at 15 Hz, and the first image aligns with the integer second in the IMU time frame. The camera internal clock timestamp of the first image is also stored and used as the base stamp to calculate the incremental time differences for the following images. Note that this scheme assumes that the total flight time of the drone is short enough that the camera internal clock and IMU internal clock does not drift too much after aligned at the beginning. And we do confirm this is the case for the DS drones with this about 15 minutes of flight time. This time synchronization scheme avoids the modifying system clock, which is the NUC computer time. This usually takes time when syncing through tools like Crony and potentially disrupt other processes that rely on the computer system time. This is especially important when launching the drones autonomously in a field within a short period of time. Now let's move on to the image quality. The image quality is crucial for visual odometry systems. To get the best out of our sensor, we did some custom tuning to the image quality. In this section, we'll present the camera model as well as an image brightness adjustment to achieve good image quality. The main camera sensor on DS drones is the UI camera. It has a global shutter sensor instead of a rolling shutter. So comparing with its Intel RealSense counterparts on the ground vehicles, the global shuttering sensor reduces the skew of the objects in the image under fast motion. So without an online compensation for rolling shutter effects, global shutter cameras are considered to be better choices for state estimation purposes. So on the bottom image, we can see an example of the skewed effects for rolling shutter camera. We choose a wide angle lens, fisheye lens for the camera, which gives us roughly about 195 horizontal vertical field of view. However, due to the size of the sensor, there are some cutoff on the top and bottom of the image, but the overall field of view satisfies the requirement and gives us a better view of the scene. To model the lens for BIO purposes, we opt to use a pinhole camera model with an equidistance distortion model. The equidistance model distortion can model our lens distortion pretty well. So here is the comparison of the original image and the undistorted image. We can see on the undistorted image, the straight edges are straight instead of curved as shown in the original image. So this shows that this distortion is successfully recovered. To further enhance the image quality from the camera, we apply an image brightness adjustment process after the raw image acquisition. With the raw images, we observe that there are regions with unbalanced brightness, meaning that the brightness values are clustered to the lower or higher regions of the dynamic range. This effect can be caused by inaccurate imaging sensor or severe lens fallout effect. So here, as in the example image, we can see that the ceiling and on the edge of the image, it is very dark. And the pixel value histogram also shows the same. A lot of pixels are clustered to the lower end of the dynamic range. So to reduce this effect, we propose to use an image brightness lookup table to remap the original raw image pixel values to adjusted values that will provide a more balanced image. So here is the steps that we took to do this remap. First of all, we crop the center of region, crop the center region of interest of the image to avoid taking into account of the invalid black edges from the fisheye lens. And then we calculate the histogram of the grayscale brightness image within the ROI, which is shown in the previous slide. And then we'll calculate the remap lookup table curve by doing a cumulative sum of the histogram followed by normalization. The resulting curve, which is shown on the figure on the right, should theoretically stretch or shrink the original histogram to use the whole dynamic range. And finally, we apply the remap a lookup table to each of the RGB channels of the image. So as we can see, the adjusted image histogram shows a better distribution of pixels across all of the dynamic range. So here are the comparisons of 3 sets of images before and after the lookup table adjustment. We can observe that the images after the adjustment show better contrast in the original dark regions. In practice, the lookup table application to image is done on camera hardware, which does not incur additional computational overhead. And another advantage of using camera hardware processing is that it has access to the raw 12-bit image. So instead of output 8-bit image, instead of the output 8-bit image, which gives us more dynamic range to the image for more information. We also observed that instead of calculating a new lookup table for each of the new frame, a fixed lookup table calculated on a representative sample image can still achieve significantly better result and reduce computation. Okay, now we finish up with the hardware system. Let's move on to the approach. We will discuss the degeneracy and failure detection for LiDAR and VIO methods first. Let's start with the LiDAR odometry degeneracy. The main failure mode for LiDAR odometry is geometrically degenerated environments. So the reason for LiDAR odometry to suffer in such environments is because the point cloud does not provide enough constraints in one or more directions when doing SAP or scan-to-map feature matching. For the shaft environment, for example, Z directions is not well constrained, since no LiDAR points in vertical direction. We will detect the LiDAR odometry degeneracy from two metrics. The first one is the optimization constraint analysis, and the second one is a 3D feature distribution analysis. For the LiDAR optimization constraint analysis, we first think about non-linear least square optimization problem. Most of the methods, like Gauss-Newton or Levenberg-Marquardt, usually first locally linearize the system based on the sensor measurement model and optimization parameters. Then we will investigate the linear problem of the equation on the right. So on the bottom figure, we show that an illustration of a well-constrained, which is figure A, and the degenerated problem for figure B. Black lines are constraints, and the green points is a true solution of the problem. For the degenerated case, the constraints are mostly parallel to each other, and the solution can slide on the direction of the blue error, leading to a bad estimation. So this is a work from previous work from Zhang Ji. He proposes that the eigenvalues of the information matrix can represent the quality of the optimization problem. The information matrix, which is shown in the middle. However, in our degeneracy module adopts similar idea. However, we observe that it's difficult to set a minimum threshold, eigenvalue threshold, as they tend to change in different environments. So we adopt a condition number of the information matrix, which is defined by the maximum and minimum, the ratio of the maximum and the minimum eigenvalue of the information matrix. This is under the assumption that when the problem is ill-constrained, one or more of the eigenvalues should have much more smaller value than the rest of the well-constrained directions. Thus, the condition number of the information matrix should be very large in degenerated environment. And finally, we use the inverse of the condition number, so that the larger the value, the better the state of the estimator. Then let's move on to the 3D feature spatial distribution metric. Since the laser mapping module of the LiDAR-Inertial odometry uses 3D features to do point-to-point, point-to-edge, and point-to-plane feature matching, the spatial distribution of the 3D features contain a lot of information regarding the degeneracy of the environment. For the feature distribution analysis, we want to categorize the features to most constrained contributing directions. So here we mainly consider the point-to-plane distance minimization and its constraints on the transformation parameters. So let's first consider a new scan point P and its corresponding map point Q. We define the error function that minimizes the point-to-plane distance as the first equation, where R and T is the rotation translation parameters to be optimized respectively. And N is the normal vector of the plane patch around the point Q. Then we can know how much the point-to-plane distance will change with the delta transformation with the next equation. So with that equation and the figure on the bottom, it's easy to see that the normal direction N that is perpendicular to the translation T, delta T, or a vector P cross N that is perpendicular to the rotation direction will not contribute to the 3D feature alignment. Then we can characterize 3D features contribution to the constrained directions in translation or rotation separately under the robot's ego frame. And here, AX, AY, and then AZ are the three axes of the robot's ego frame. Thus, we can categorize each planar 3D point into most constrained contributing directions. We assume that a well-constrained configuration have a roughly equal number of points in each most constrained directions, and vice versa. So here is a short example of the characterization of different 3D planar points. So the red represents the X point, a green represents a Y point, and blue represents a Z point. So we roughly see any Z points here because there is not much. Okay, now let's move on to the visual odometry degeneracy. Visual odometry usually suffers due to textureless environment, under or overexposure, or bad illumination. This introduces challenges to the feature extractor and front-end processing. These failures can often be detected from the stability of feature tracking. In this thesis, we propose to use feature tracking quality as well as monitoring the feature reprojection error in a sliding window to detect the VIO status. We also monitor the velocity and IMU bias estimated by VIO to check for abnormal estimations. So on the front end, the good features to track is used for feature extraction, and then the KLT method is used to track the extracted features across multiple keyframes. While the front end tries to maintain a certain number of features, tracking for unstable features will fail in suboptimal cases, which is shown on the right, where the red points are the stable features and blue points are the new or unstable features. So thus we monitor the number of well-tracked features after performing each KLT tracking between frames. A well-illuminated and textured environment should have over 120 features in a frame, and if the number falls under 30, we consider the VIO results to be not well conditioned. These thresholds are set from our experience. We also keep track of feature reprojection error to monitor VIO status. As shown in figure, features are added to the optimization problem as the inverse step formulations, where a single parameter is added to the problem for each feature. For the reprojection error monitor, we use features' first observation frame of the sliding window and reproject them to the last frame in a window shown in the figure. So now consider the feature first observed in frame I and then track across multiple frames to frame J. We first get the 3D coordinate of the feature using the inverse step to propose the first camera frame, and then transform to the last frame and do the reprojection. We then need a metric to determine if the reprojection error is abnormal. So inspired by the feature selection method in OrbSlam, here we use a chi-square distribution to model if a feature has an outlier reprojection error. And then we monitor the percentage of the currently tracked features that are outliers after each optimization. We use a 2-degree of freedom chi-square distribution since our area is measured in both row and column pixel locations on the image plane. We assume the row and column measurements are independent to each other so that the chi-square distribution holds. We choose a 1 pixel measurement error and a 95% confidence level for the measurement to be an inlier. And a chi-square table lookup gives up about 5.99 pixels as our threshold error. Now, if more than 75% of currently tracked features in the frame are categorized as outliers, we will discard the VIO estimates in the final pipeline. And finally, aside from the above two methods, we also detect potential VIO failure with the estimated robot motion results. We have set the following parameters for our system and based on controller and experiments. Okay, now let's move on to the VIO pipeline. So here we will discuss our approach from 3 aspects. First, I will show the VIO overall framework, and then the initialization and LiDAR depth enhancement components of the VIO are shown in more detail. First, our depth enhanced visual odometry is based on an open source VIO system, VINCE model. We formulate the VIO as a sliding window optimization based system with tightly coupled visual and IMU measurements. The VIO jointly estimates for the state vector of position, velocity, and orientation of the latest body frame, as well as the accelerometer and gyroscope biases. On the front end, we use the Xi-Tomasi features as our feature extractor. And as mentioned above, after features are extracted, a KLT tracking is performed on each of them. After the feature tracking, features with failed tracking status will be discarded, and we will extract new features in the image frame. Then the image feature undistortion and ransack outlier rejection with a fundamental matrix model is performed. For the well-tracked 2D features, they will be added to the optimization backend using an inverse depth feature formulation. And for the newly tracked features, we will perform triangulation, or in our case, LiDAR depth initialization to initialize the depth for the features. IMU measurements are added to the optimization problem as IMU measurement residuals in a pre-integration fashion. IMU pre-integration reformulates IMU integration process by integrating using IMU body frame, which will reduce our need for repropagating IMU states with constantly changing camera poses in the optimization process. Now let's move on to the VIO initialization procedure. For the original vision-only system, 2 steps are performed to initialize the estimator. First, a sliding window vision-only structural motion to recover the camera poses and feature structure. And second, a visual inertial alignment to recover the gravity direction, velocity, and of course the correct scale of the structure. For our VIO setup, we added an additional method for VIO initialization when LiDAR-Inertial odometry information is available. Vision-only initialization method depends heavily on the initial movement of the sensor in order to recover the crest scale information. It will require enough IMU acceleration excitation for initialization. However, in practice, we often encounter constant velocity robot motion in our system. To improve the robustness of our VIO system, we leverage the state estimation from LiDAR-Inertial odometry if it is available at the time that VIO tries to initialize. Instead of going through the structure from motion and visual inertial alignment, we directly assign system states from LiDAR-Inertial odometry, and along with IMU acceleration and gyroscope bias, which is shown in the figure on the right. After system states are assigned, we will need to initialize all the feature depth by doing a triangulation step. Since a robust triangulation requires enough disparity, we also do a view parallax check before performing the triangulation, discarding the second newest frame if the camera is stationary, and keep sliding the initialization window when enough movement is detected. Okay, now finally move on to the LiDAR depth enhancement method. So since we have LiDAR depth available, the direct depth measurement is considered to have better accuracy than VIO. We would like to use this information to improve the performance of VIO. To find the 2D features LiDAR depth, we first project the 3D LiDAR points onto a unisphere. And then we will find the 3 closest neighbors of the point intersection between the feature ray and the unisphere using a KD tree search. Finally, the feature's 3D points will be recovered by intersecting the feature's ray with the plane of the 3 LiDAR points in Euclidean space. We also reject the LiDAR depth when the maximum and the minimum depth of the 3 points have a difference of more than 2 meters. This is because we are accumulating the LiDAR cloud frames for 5 seconds, and previous frames can have depth that are no longer visible to the camera. Here we show a feature depth assignment example. On the left are the 2D features of the VIO, and blue points are the features with depths assigned from LiDAR, and the green points are the triangulated depth points. Finally, let's move on to the LiDAR visual inertial odometry pipeline. So we base our full pipeline on the LiDAR-only version of super odometry. In addition to the original system, two modules are added. A VIO system that is running concurrently with the LiDAR odometry, and the degeneracy detection module that controls the odometry source in LiDAR odometry optimization. We'll mainly discuss two ways to fuse the VIO pulses. The first one is to use it as a laser mapping initial guess, and the second one is added as an absolute pulse vector to the laser mapping optimization. So here are the differences of the three methods in laser mapping components. To add it, so for the laser mapping module performs scan to map registration, and a good initial guess can increase the robustness of the registration, as well as reduce the computational load by decreasing the necessary iteration number. So for LOM, only IMU orientation are used for initial guess. And for LiDAR-only super odometry, both orientation translation from IMU odometry is used as initial guess. For our system, we choose to use whether IMU odometry from LiDAR or visual odometry as initial guess, depending on the degeneracy situation of the LiDAR odometry. So in the event of LiDAR odometry degeneracy, we will first transform the new scans using the latest IMU, using the latest VIO state estimation as a state estimation, and then do the scan to map registration. For the absolute pulse factor, we directly added the VIO relative pulse to the optimization as an error term. So in practice, we observed that only providing an initial guess, we still cannot obtain the accurate pulse when the constraint is just lacking. Thus, we need to provide a more constraint to the laser mapping component. And for the original LiDAR odometry implementation, the error function are the point-to-point, point-to-line, and point-to-plane errors. And here we added the IMU pulse error to the optimization using the translation and rotation differences between the estimation and VIO odometry. Then we add the absolute pulse residual to the total error function with the weighted information matrix defined as following. So here, the CLX, CLY, and CLZ are the coefficient in the so those coefficient in the translation part are the LiDAR feature distribution degeneracy score. So with the higher confidence in LiDAR odometry, which with the coefficient closer to 1, a smaller effect of VIO pulse will play in the optimization. From our experiments, we also find out we get better performance with the uniform weight for distribution. So this might be due to a not so accurate rotation degeneracy coefficient estimation. And finally, let's move on to the experiments. We will talk about the experiments from the degeneracy as well as the final pipeline. So first, for the LiDAR degeneracy experiments, we'll run our state estimation through multiple challenging data sets where LiDAR odometry suffers from insufficient geometric constraints. We also have some expected degeneracy directions. For example, for the elevator shaft, we expected degeneracy in Z direction. In the experiment, we plot the 3D feature degeneracy factors as well as the optimization condition number as our robot traverses through each of the environment. So for the elevator shaft, the drone flies up and down vertically. Due to the constrained space of the shaft, the Valentine scans have very limited vertical field of view, causing a degeneracy of motion in Z direction. So the first two plot shows the feature distribution metric in both translation and rotation. And the last plot shows the condition number of the information matrix. So as we can see, we do see a translation uncertainty reported in Z direction for translation. And the degeneracy is detected for roll and pitch. The condition, however, we do see some disagreements between the condition number and the feature spatial distribution, where the condition number reported degeneracy only in translation, which is shown in the red line, but not rotation. So we believe this is because the feature distribution method is conservative, as it considering each feature to only contributes one main direction. But in the actual case, a single feature can provide constraints to multiple directions. And for the long corridor data set, robot moves from one end to the other and return back to the starting point. For feature distribution metric, we observe degeneracy in the X direction, which is the robot heading direction when it's traveling through the corridor, both departing and returning to the starting point. We also see the rise of confidence in X and the decline in Y at the middle of the plot, where the robot yaws in place. This makes sense because while the robot is turning, the degeneracy direction, which is along the corridor, switches from X to Y and then back to X when the robot is returning home. So similar case in rotation plot where the roll movement is under constraint when the robot is traveling across along the corridor. And when the robot is turning back, we can see degenerate rotation axis changes from roll to pitch and then back to roll. So here is the Lauren Caverns stairs dataset. We want to show that the degeneracy in a larger underground environments, natural cave. So we see similar results at the long corridor where X direction is degenerated. So here is the correspondence of the final map and the plot that we shown earlier. We can see the X direction reports a low constraint in the corridor-like environments. So finally, the Gates garage data shows an example of a geometrically well-structured scenarios where constraints presented in all direction of the LiDAR frame. And we do see this is the case from our degeneracy response. We also do some simulation experiments. We set up a gazebo world using drone with a similar sensor setup. Here we tested the corridor and the shaft environment. And we do see similar responses as the real world data. For both, on the left is the corridor data set, and on the right is the plot of the shaft data set. Next, we will show the failure detection for visual odometry in different data sets that represent many failure cases. So that includes poor illumination, aggressive motion. We also encountered initialization failure, which we'll show later. So in this data set, the drone enters a dark room 3 times, and we can observe that the low feature tracking status when it encounters a bad image quality. Here in this small constraint, small opening data set, the drone flew autonomously through a tight opening. And during the flight, the drone bumped into the wall and rotates aggressively in the constrained space, as shown in the video. We can see the reprojection error and the well-tracked feature number becomes low when a drone is under aggressive motion. Here in the hallway data set, the drone was picked up from the ground and hand carried in the hallway. We intentionally free run the camera without any external trigger, making a suboptimal time synchronization between the sensors. So the odometry fails to initialize at the beginning in the visual inertial alignment stage. The trajectory drifts significantly and out of scale with out of scale feature depth estimation. We can see that while the well-tracked feature number doesn't reflect the situation, the reprojection error can detect the degraded estimation. Finally, we experiment our detection method in the UROC dataset. This data aims to show the response in a normal situation. And both the reprojection error and well-tracked feature number shows a good status. Finally, we will present the results from the final visual-aided LiDAR-Inertial odometry pipeline. More specifically, we will show the mapping and trajectory results in the challenging environments and the trajectory quantitative analysis in simulation. So here I will play this video for the demo. Okay, and for the trajectory error simulation, in simulation, we reuse the same world described in the above and compare the absolute trajectory error against the ground truth trajectory. And for the long corridor data set, we can see that our method, which is showing the green trajectory, can better recover the degenerate direction along the corridor. And for the Z direction, the shaft data set, we can see that the Z direction is much better recovered, while the XY have a little bit more error. So here is the table of the ATE shown in the data set. We can see that our method performed slightly worse in normal conditions. This is because VIO estimation are still added to the system when not necessary. However, in the degenerated directions, we show much better results. So here are the conclusion of today's talk. We showed a degeneracy and failure detection method for both LiDAR and visual odometry systems. A hardware and software design of the LiDAR depth enhanced the visual inertial odometry system is also presented. And finally, a visual aided LiDAR inertial odometry pipeline shows much better results in challenging environments. Yeah, that's pretty much all. I would like to thank my committee for giving me useful advice during the thesis, as well as special thanks to Shivo and Lucas, which pretty much guided me through the entire process. And finally, to all the talented researchers and engineers in Air Lab and Team Explorer, it is my honor to have been working with you guys, and hopefully we get great results 40 days later. And that's it. Thank you, everybody. I'm open to questions.
Thanks, Henry. Thanks for the nice talk. Yeah, maybe we can open up to some questions.
I guess I can start with a question here. So Yeah, I did like that you're looking into the degeneracy, and then using the degeneracy measure later to assign weights to the different odometries. But then you also mentioned that part of it, like the rotation, you did end up using a fixed weight because of poor degeneracy measure. So it would be interesting to revisit that and like how reliable are the degeneracy measures? When do they fail?
So yeah, this is some of the problem that we've seen in our current implementation. So for translation, we do see pretty consistent performance, but for rotation, I think as I sort of explained earlier, that we think that so currently we assign a single feature to the most constrained direction. So each feature corresponds to a single rotation constraint. But we don't think this is the actual case. And in the future, we think we can better categorize each feature maybe to multiple constraint directions using by doing a more detailed analysis to the eigenvalues to the coefficients that we sort of discussed above. So yeah, there are some room for improvement for sure. But for translation, we do see pretty consistent performance with our current implementation.
Yeah, I guess translation is generally not so well determined using IMU only. So for the rotation part, you could also maybe just look at IMU over a very short time frame.
Yes. However, I think in some of the very degenerate cases, so for example, if the drone sort of fly through a tube or something like that, where the rotation axis along the tube that is just entirely degenerate, maybe the IMU could still drift in that case, but I guess the orientation from IMU is also pretty good, so maybe that is.
Oh yeah, since you wouldn't get any update over a longer time frame, so you would.
Yes.
Correct. Yeah. So if you just rely on IMU at that point, that doesn't work. Okay.
So I have maybe a bit more of a basic clarification question. So how does a degeneracy get used in the SLAM system again? Does it get assigned as a factor or switched on or off? Or
I guess this is my bad to not explain it clearly, but so we do have a switch based on the condition number from the LiDAR odometry. So basically, when either the translation or rotation, when the translation condition number becomes very low, we start to use VIO pulse vectors, and then the exact weight is assigned using the 3D feature distribution coefficients as shown here.
Okay. So there's basically a discrete switch based only on the LiDAR.
Yes.
And then
in the meantime, we also check whether VIO is healthy using the VIO.
Sure.
Yeah.
Yes. And then how much you weigh is based on the feature distribution.
Yes.
Okay.
So this sort of
Henry.
Yeah.
Okay. So I just have a question regarding the conditional number.
Yeah.
I wonder how sensitive is this conditional number to the number of points. Let's say you observe the 1,000 points on the ground constraining your Z position, but only maybe 100 points on your left and right restraining X and Y position. And will that affect your conditional number along different, in this specific case? In reality, maybe 100 points is not so bad to constrain your robot pose, right?
Yeah. That is a great question. I haven't actually do any experiments on that. Yeah, but I think that leads to whether the difference in future points will affect the optimization process. But I think you raised a good point that maybe a discrepancy between the number of points in different directions doesn't necessarily mean a degenerated case. So yeah, I think maybe we can do some more specific checking on, like, even though the ratio between the constraints, number of points in directions are not well conditioned, but in the meantime, maybe we can set a minimum threshold of points in each directions to. So, for example, it's more than 100. Maybe it is already enough to constrain that direction. Yeah, I think that is actually a good point. Thanks.
So does your system solve all the problems? Or what would you do differently in a future development? So what would you add? What would you do differently?
Yeah, for sure. So it definitely does not solve all the problem. I doubt that ever happens. But so I think, first of all, we definitely need a better LiDAR rotation degeneracy estimation as shown, because our current method isn't as robust as we expected. And then we also encounter a lot of CPU usage issues that we're facing when trying to deploy on a drone. So this mainly because we're adding an entire VIO component to the system, and we just don't have enough compute to support that. So of course, I think we can definitely do some more optimization in that area to have like actual system deployment. And something to extend on current pipeline is that it's sort of like a good to have. I think it's more modalities. So we do see there are cases where both LiDAR and visual does not provide very good constraints. So like in that case, maybe we can add thermal odometry or something like that, or wheel odometry to the pipeline to further constrain the problem. So yeah, I think that is 3 of the main future works that can be focused on.
Okay, just to follow up on the last one of these.
Yes.
Would it make sense to add multiple cameras? So for example, looking in different directions, and could you easily incorporate those?
Yeah, for sure. I think, I guess first of all, I think that's definitely going to help. We do see some previous work from Josh from RPL that doing multiple set of stereos for visual odometry and performs better results. So definitely can increase the robustness. On how to implement it specifically, so if we adopt the current sort of implementation, then I guess we will do degeneracy detection separately on the 2 sets of maybe multiple directions of camera views, and then add those constraints to the laser mapping module based on the VIO degeneracy score. So yeah, we will have to introduce the VIO degeneracy score to the weighting function of the laser in the laser mapping error phase.
Yeah, there's actually an interesting question there. So Josh basically looked at the cameras simultaneously and combines features from those.
Yeah.
So the question is it more robust if you treat them independently and look at degeneracy for each one of these separately?
I think there's definitely an advantage of combining multiple directions, because I guess you can reuse some of the features across stereo pairs. But I guess that also introduce some uncertainties, especially when one of the direction is not in well conditioned. So yeah, I think maybe the Josh method can have better accuracy, but like if we treat it separately, we can have better robustness. But again, that is my guess. I'll have to experiment with that.
Yeah, that sounds reasonable. That would be interesting to experimentally try out. Okay, thanks.
Thank you.
Yeah, actually, kind of following up on this, the results you showed basically kind of, you said, okay, it's less accurate but more robust when you add the cameras.
Yeah.
So, do you have an idea of how we could kind of overcome that problem?
Yeah. So I guess with our current formulation, then the obvious way to go is to get a better, like a more stable degeneracy detection. So here, I think in the worst performance in normal cases, we usually see that like the degeneracy score oscillates and sometimes it falls under the threshold for a very short period of time. And during that time, the VIO estimates are added, degrading, sort of degrading the LiDAR performance. So I guess a quick implementation, we can do some average filtering on the degeneracy scores. This will sort of introduce some lag in actual degenerate cases, but I think we can reduce the effect of like the oscillation of the degeneracy score in normal cases. So yeah,
and I mean it's basically the visual odometry has a much higher drift rate, and so anytime you add it, it basically adds noise. Is that kind of what happens?
Sort of comparing.
So is there? I guess I'm wondering, is that also, if we would do a more careful modeling of the uncertainties, could that be reflected in that and not potentially degraded as much? Like, if you know that, I don't know, the drift rates, 10 times higher or whatever it is, and when we combine it, would then in the degenerate situation, the LiDAR odometry still think it's too confident, or like what's happening?
Yeah, I think there's definitely a lot of things that we can do in the weights when the VIO gets added. Considering the drift rates of VIO, I think could be an approach here. But I guess the thing is that still, like if the degeneracy detection consider the current environment is degenerated, then I guess it's hard for it to figure out like whether it's like true degeneracy or not. So I guess in the direction of degeneracy, it will still uses the VIO estimates. But on other well-constrained directions, maybe we can consider better weighting functions of the VIO vectors when adding to the laser mapping odometry.
Okay. And then just one last question is, so is there, it seems like there's a little bit of information reuse going on, like double potential kind of double counting. Like for example, the IMU probably gets used in the visual odometry and gets used in the LiDAR odometry, and then again in the super odometry, I guess.
Yeah.
So,
yeah, that's true. So yeah, that is the point. So currently, our system is sort of separated to very big components. So like for visual odometry, we actually run a full VIO pipeline, and then for laser, we also do a LiDAR-Inertial odometry pipeline. So I think the system can be better integrated together. like what Subterranean actually proposes. So like have the IMU in the middle and only added the laser only and vision only constraints to the problem. So I think that could be like a cleaner setup. But the thing is, so for IMU processing, doesn't take a lot of computation. So the pre-integration can probably run like a couple 100,000 hertz. Like it's not a lot of computation not a lot in terms of computation. So
right, I guess the worry would be more that in terms of, for example, covariances or something like this, that you become overconfident when you start reusing the same information.
Yeah, we do see that is the case. Like for example, when LiDAR odometry is LiDAR, so our degeneracy currently only analysis the LiDAR measurements. But when we're looking at the whole optimization problem, when the IMU factors are added, you sometimes loses the degeneracy direction. So yeah, I guess. So currently we do the degeneracy very carefully, like only use the LiDAR measurement and the visual measurements. But I guess by doing it all together, like using the VIO and the LIO pipeline, the degeneracy score doesn't really reflect the estimator's status. So if we sort of separate those, like using a more like a cleaner pipeline with the IMU in the center and LiDAR and visual added to the IMU, then the degeneracy score can better estimate the actual status of the estimator.
Okay, cool.
Yeah, thanks.
Any other questions from the audience? No questions. Okay.